Primary production is the amount of solar energy that is captured by producers and turned into chemical energy. And secondary production is the amount of that chemical energy that is converted into new biomass, so the next trophic level up. So how much of that producer biomass that was produced by primary production is then moved up to herbivores, and how many of those herbivores are moved up to carnivores, etc., etc. And those numbers aren't the same. Secondary production is much, much lower. Why is that? Well, it's because our production efficiency is not 100%, right? It's essentially because a lot of the energy that you acquire by eating the trophic level below you is then used for cellular respiration, and a lot of that is lost then as heat. So when a caterpillar feeds on a leaf, about 1/6 of the leaf's energy is used for secondary production. The rest is used for other things. And so production efficiency is this net secondary production over the assimilation of primary production, and then times 100% to get your percent. And it might be easier to look at this visually. So we have a caterpillar eating a plant, and let's say there are 200 joules of plant, right? 100 joules of that, first of all, is just going to be lost as feces. Right? That doesn't mean it's gone from the ecosystem, because you have worms and fungus, etc., that it can capture some of those calories, but they're not going to move into the caterpillar, right? Of the remaining 100 that is not lost as feces, 67 of those 100 are going to be used for cellular respiration and lost as heat, and only 33 are used for new biomass, meaning to build the caterpillar. And it's only the stuff that's used to build the caterpillar that can then be moved into the next trophic level up. So the bird that eats the caterpillar, for instance. Those efficiencies depend upon the organism. Birds and mammals have very low efficiencies because of endothermy. We use a lot of that energy for cellular respiration just to maintain our body heat. Fish have production efficiencies of around 10% or more, and insects and microorganisms are often at 40%, which is very high. But typically this efficiency of movement of energy from one trophic level to the next is about 10%. It's just a good rule of thumb. It can range to about 5 to up to 20, more or less, but usually, just as a rule of thumb, about 10% is a good back-of-the-envelope way to calculate this stuff. And this 90% loss is amplified over trophic levels. So by the time you get to a tertiary consumer, only about 0.1% of the chemical energy that was fixed by photosynthesis in that primary producer is going to reach there. And so you end up with this pyramid of net production that shows you the loss of energy at each step of the food chain. So out of, let's say, 1,000,000 joules of sunlight, about 10,000 is captured by primary producers. And from then on up, we take about 10% of it each step to the next stage, right? So 1,000 joules for primary consumers, your herbivores, then about 100 joules for your carnivores, your secondary consumers, and then about 10 joules for your tertiary consumers. And if you have quaternary consumers, right, then you're at 1 joule per 10,000 joules captured by primary producers, right? So this begins to show you why when you go outside and look around, it's mostly plants. You see very few, coyotes or hawks or pumas, right? You see them occasionally, but you see a lot more primary producers, and then a lot more like insects, for instance, or grazers. Typically, because there's less energy moving up a trophic level, you have less biomass at that trophic level. And this is also why, for instance, a lot of people who are picky about their diets and have ecological concerns tend to be plant eaters, right? So a lot of vegetarians are vegetarians not just because they might have ideas of cruelty to animals in the animal industry or the agricultural industry, but because eating plants is a much more efficient use of the world's resources. This isn't me preaching. I love a good steak, but it's much, much less efficient to eat animals. And this is also why, it's very, very wasteful if you dine on tiger, right? If tiger is your favorite organism to eat. Now, there are examples of aquatic ecosystems that have inverted biomass pyramids, at least at the lowest levels, because the primary producers, the phytoplankton, are born and are eaten so quickly that even though more of them are produced over time, at any given moment, there are fewer of them alive in terms of biomass than there are zooplankton. Now we've talked a lot about how energy flows through an ecosystem. Again, it eventually lost its heat, and we have to keep replenishing it from the sun, and if the sun turned off, we would all be gone pretty quickly. But now I want to talk a little bit about how nutrients, chemical elements, which are matter, cycle within an ecosystem. There are a lot of different examples of important biogeochemical cycles. Carbon, oxygen, sulfur, nitrogen, these are all things that become gases, and so they have very global cycles, because once you become a gas and you get to the atmosphere, you can cycle all around the planet. Things like phosphorus, potassium, and calcium don't tend to become gases, and so they tend to cycle in more local areas, especially in terrestrial ecosystems. When they get into the oceans, then you can have more broad cycling through currents as they dissolve in the water. Typically, in nutrient cycling, you have reservoirs where these elements will hang out for a little while, sometimes a long while, sometimes a little while, and then processes that transfer these elements between reservoirs. And those reservoirs can be organic, right? Right now, I am a reservoir for a lot of things: nitrogen, phosphorus, water, and inorganic reservoirs like oceans, for instance, or coal is an inorganic reservoir for carbon. How do these elements go from reservoir to reservoir? Well, living organisms are organic reservoirs, and those elements can move into inorganic, unavailable reservoirs as peat, coal, oil through fossilization, right? They can become inorganic reservoir, they can occupy an inorganic atmospheric reservoir by breathing out carbon dioxide, for instance, or decomposing and releasing nitrogen, which can be denitrified by denitrifying bacteria and go back to the atmosphere, etc., etc. Right? Water can evaporate, right, from ocean or a lake and go up into the atmosphere and move around. Right? These are all ways that things can move from one reservoir to another. Minerals in rocks, that's a reservoir. It can, through erosion, through wind or rain, can then go off into a body of water, for instance, in runoff, and that's movement from one reservoir to another. So I'm going to talk about a few important ones: carbon, nitrogen, phosphorus, and water, and I'm going to talk about their biological importance, the forms in which they tend to be available or unavailable, and organic or inorganic in terms of reservoirs, the major reservoirs, and how they are processed from one reservoir to another. The water cycle you're probably pretty familiar with. The vast majority of water is contained in the oceans, 97%. The other 3% is fresh water, and 2% of that is in glaciers and polar ice caps, and only 1% is in lakes, rivers, and groundwater, and that's mostly what we're talking about when we're talking about drinking water, for instance. It tends to move around through evaporation, condensation, transpiration, precipitation, etc. Water in oceans or lakes or rivers, bodies of water, especially the ocean because it's so huge, the water tends to move from those reservoirs through evaporation, becomes clouds. Now it's in the atmosphere, it can move all over the place. Those clouds are condensed water, and when they become dense enough, they drop the water over the land. That water can be taken up by organic reservoirs like plants and animals. It can percolate through the soil into groundwater, which is a very common reservoir. Runoff into groundwater, for instance, and then from my breath or evapotranspiration through plants, it can also go back up into the clouds, and that's the main movement, right, is in clouds. We are carbon-based life forms, so carbon is also very important, and it gets captured from the atmosphere by photosynthesis and trapped into organic reservoirs, right, in the form of autotrophs, and heterotrophs can consume that, like us, we can eat plants. And then it is in organic reservoirs like organisms, also inorganic reservoirs like fossil fuels, right, and soils and sediments and solutes in the ocean, and then it's taken up and released by cellular respiration. When I breathe out, that CO2 goes up into the air. So broadly, it tends to get fixed by photosynthesis and released through cellular respiration. And sometimes it passes in between there from, a primary consumer to a secondary consumer to a tertiary consumer, or it goes into the ground through dead animals and decomposition, and sometimes that can get locked into rocks, right, sedimentary rocks, or, again, things like fossil fuels. And burning of these fossil fuels has recently, last 100, 150 years, released, especially the last couple of decades, a lot of this carbon that would have been locked up for a long, long period of time. And so it's really thrown off this carbon cycle in a way that we haven't seen, at a speed that we haven't seen in recorded time. And that has obviously implications for our global temperature. In terms of nitrogen cycling, nitrogen is mostly in the atmosphere, right? The vast majority of the atmosphere is nitrogen, but it's an N2, and it's two nitrogen molecules held together by that triple bond we've talked about, and it's really, really hard to turn that into a usable form by life. But it flows through the atmosphere all over the Earth pretty easily. It gets fixed by nitrogen-fixing microbes, many of which are associated with plants, for instance. Some of them are in the water. You have aquatic cycling too, and essentially the way that happens is you have nitrifying bacteria that put it in the soil. It's taken up by plants, which are eaten by animals, and it cycles within there. Eventually, animals die, plants die, those are broken down, and there are also denitrifying bacteria, which take these sort of living forms, organic forms of nitrogen, I should say, and release it as N2 back in the atmosphere. And this is really the crux of the cycle. Now, we've also messed with this cycle too, in the sense that we have found out a way to artificially fix nitrogen using the Haber process. And this is an industrial fixation. We use this to make a lot of inorganic fertilizers, right? Artificial fertilizers, I should say. And we also put a lot of nitrogen back into the atmosphere through reactive gases, through industrial processes. Now, the biggest ecological impact of this doesn't have to do with the atmosphere like it does in CO2. It has to do with runoff. We're pouring a ton of nitrogen on our fields. That runs off into lakes and rivers and even oceans and creates these algal blooms that we've talked about, which can cause die-offs because they end up sucking all the oxygen out when those algae are eaten, and it can cause big dead zones in certain areas. Like we have one in the Gulf of Mexico. It's a giant, giant zone where not very much lives. Phosphate is another very, very important element, or mineral, I should say, and it's important. It's the phospho and phospholipids, and the phosphate in adenosine triphosphate, and it's found in DNA, and it tends to come from rocks, and it gets made available by the weathering of rocks, right? The erosion, and that can go into soil or sometimes water, and then that's picked up by living things. So that erosion is important. It tends to cycle locally, but if it runs off into water, again, the oceans can move it a little bit more far and wide. And then living organisms tend to die, or it tends to kind of resettle at the bottom of the ocean, and it turns back into sedimentary rock, and that's that cycle, right? It turns back into sedimentary rock. That rock is then uplifted by the processes of the earth, and then it erodes again, and then it becomes available to organic molecules one more time. Decomposers play huge roles in these cycles, especially in little sub-patterns of the cycles where they continue to make these nutrients available for more and more organisms after other organisms die, and that rate of turnover depends on things like temperature and moisture and nutrient availability, but decomposition is an essential part of that nutrient cycling for every one of those nutrients. Well, not water. Not so much water is not as important, but other things. The more rapid decomposition occurs, though, the fewer nutrients you tend to have in the soil because they're picked up so quickly. So tropical rainforests have tons of nutrients, but they get taken up so quickly from the soil because there are so many decomposers that your soil is not very rich, which is why when you burn it to grow crops like they're doing in parts of the Brazilian rainforest right now, those farms only last a few years and you have to burn some more stuff, right? Cold, wet ecosystems tend to have slower decomposition, and so they tend to have better soil for longer periods of time. Restoration ecology is a whole branch of science that is dedicated to finding ways to speed up the recovery of communities that have had disturbances, especially human-caused disturbances. One strategy is bioremediation, where you use organisms to detoxify ecosystems. So bacteria that can munch up old oil, or plants that can take up toxic metals like aluminum and things like that. And the other main strategy is biological augmentation, when you add organisms to a degraded ecosystem to help fix it. So for instance, when you have poor soil, you may add nitrogen-fixing plants to make more nitrogen available, adding fungi and bacteria to improve the soil and those mutualistic relationships with potential plants.